Okay. What I want to do is this one because it's the second exception that you need to know. Okay, there's only going to be 2 exceptions, and this is the second one. Okay, and it is what I call the ion exception. Yes? So if you see something that has a positive or negative charge, you have to repair that one. Just like you had to repair anything that's smaller than carbon, you had to make an adjustment. You have to make an adjustment for anything that's charged. So one exception is the smaller than carbon. The second exception is the ion. And then, by the way, in case I'm losing you, before we get to there, we're done. See, and notice on my cheat sheet, I put, when I go from the formula to the NASA table, I always look for 2 exceptions. I look for the less than carbon and I look for the ion because I know if those exist and I miss them, everything else is going to be wrong. And that's one of the bad things about these, is if you make a screw up here and you're asked 5 questions, you're going to miss every one of those. Every one of them. So if you're going to not learn how to do something, for Pete's sake, at least be able to get down to like the Lewis dot structure, the electronic geometry. Because you mess up on your NASA table, you have just messed up big time. Everything's wrong. And on the final exam and on your next test, you'll be given something to go through this protocol. And if you screw up the NASA table, you're going to miss 5 questions. You're going to miss about 10 or 15% of the test. So that's just, sorry, that's the way chemistry works. Okay. And a lot of science. One thing depends on another. So I'm telling you, at least you got to get really good at this Lewis dot structure, because a lot of questions will stop here. There's going to be a number of questions that will stop here. And if you know that, I think I messed mine up on the last one. Okay, well, what we want to do is we're going to worry about the exam questions at this point. Okay. So let's look at the ion exception now. Okay, so real quickly, let me get my typing and let's do this one. Yeah. Okay, so let's see if it'll give me my... Hang on, let me cut that one off. I am literally using 3 different programs here. Come on, type for me. Come on, type. Okay. So the need is equal to, I have 1 nitrogen. How many does it need? 8. And I have 3 oxygens. And how many does each of those need? 8. For a total of 32. Available. I have 1 nitrogen. How many does it have available? Ooh, I don't have that one memorized. Let me see. Nitrogen is right here. So it's in this 5th group. It's in group 5, so it needs 5. And I still have 3 oxygens. And each one needs, oh yeah, same as before, oxygens in group 6. You'll do so many of the oxygen, you'll get the hang where you can just do these almost immediately. Okay, so a total of 18, 19, 20, 21, 22, 23. Okay, so what's wrong with this picture? Here's a clue that you're in trouble, at least in intro class. This should never be odd because things paired up. As an aside, when there's an odd number there, that's called a radical. And a radical is very reactive. Those are the things that cause cancer and stuff like that in your body. You take vitamins and sometimes they'll say, antioxidant, okay? What the antioxidant is doing, some of those things that you take that are antioxidants, is they take any molecule that has an unpaired electron. See, if it's got an odd number, it means one of them's not paired up. Those things are dangerous. They are typically very, very unhealthy. And so we take other foods that will scavenge them. In other words, that will go over and like a rabid dog, it'll go over and throw them a bone. It's a molecule that when it sees a radical with an unpaired electron, it gives it an electron to calm it down. Okay? So here's the deal in this class. That's called a radical. We don't deal with radicals in intro chem. So if you get an odd number, you know you either you did something wrong, or you haven't gone far enough. And in this case, you haven't gone far enough. Why? Because what you've given me is the available line for what? NO3, not NO3 minus. If I ask you the structure for nitrogen trioxide, you would stop here. Yes? Why? Because you did one nitrogen, one. But what do we have here? We've got a negative charge there, right? So what does the negative charge mean? I've got one extra electron. So what do I have to do to this 23? I've got 5 electrons from the N. I've got 18 electrons from the O's. Plus I have what? 1. Oh, please let me go back. Let me go back. Come on. There it is. Plus, I have 1 electron that's extra for a total of 24. And that is one of the great missed questions on an exam, because people will miss correcting for the ion. You have to look and see, do I have carbon? Do I have anything less than carbon, or do I have an ion? You correct for the less than carbon at the needs line. You correct for the ion at the available line. And now everything else is just normal once you've corrected that. And I'll show you how this works. Okay, so what is my shared line? My shared line is equal to 32 minus 24, which is equal to 8. Yes? And what's that really going to give me? Now I'm gonna start making some shortcuts. That's going to give me what? 4 bonding pairs, right? Okay. And finally, I have alone electrons. And how many do I have of that? Let me see. I've got 24 minus 8 is equal to what? 16? That sounds good. So I have 16. Does it sound good? Actually, I'm not sure. I'm not good in my head. Okay. So there we go. So I'm guessing I have 8 lone pairs. Okay. NASA table, done. Skeleton, I've got an N and 3 oxygens. N is the least electronegative. N is furthest away from fluorine. Oxygen is right next to it. N is 2 away. So the thing furthest away from fluorine is nitrogen. So I'm going to guess that my skeleton looks like this. Looks like this. I'm going to have an N, and I have to correct for the opacity too, don't I? Take that back. Boom. I've got an N. This is just my skeleton, and I have 3 O's. It doesn't matter what angle or where you put them. I normally just put them as far apart as possible. Later on, you'll learn what it really looks like. Does everybody see that's the skeleton? I've got the least electronegative thing in the center. I've got everything else hanging off of it. And I have everything bonded by a single bonding pair. Okay, let's go back and play. I have 4 bonding pairs. How many do I have already? 3. My skeleton has 3, so I need to place 1 more. Since all these are the same, you could have placed it in between any one of them. And now I have 1, 2, 3, 4 placed, and this is done. I've got those placed. Now I need to place 6 lone pairs. How do we do those? Start from the what? Outside in. So let's do that. Okay, I'll start with this one. Outside in. How many does this feel? 1, 2, 3, 4, 5, 6, 7, 8. Why did I stop at 8? Because right there, you told me to stop at 8. Each oxygen needs 8. That one has 8. How about this one? 1, 2, 3, 4, 5, 6, 7, 8. Now I've about lost track. How many lone pairs have I placed so far? 1, 2. how many lone, oh, geez, nobody was going to tell me. Okay, 16 divided by 2 is what? I'm going to go with 8. Okay, how did I know that? Because I could look and see. Okay, so let me show you how I knew that. That was an honest mistake, but okay. So when I had 6 there, that's 6 lone pairs, right? So I'm done. But guess what? How many electrons does this feel, that oxygen? Can you see it only feels 4? So I knew it needed some more. I knew I was short some electrons because it's got to get up to 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8. And now look how many lone pairs we placed. 1, 2, 3 pairs. 4, 5, 6, 7, 8. I go around the outside and make sure all that's met, and then I see if there's any left over. I placed 8 lone pairs, and that's all I had was 8, so I'm not going to dump anything on the central atom. Nothing. Nada. So there we go. So I now have this done. Here's the only trick here. Now I know there's a negative charge floating around in there somewhere, but I don't know where it's at. So here's what you're supposed to do. You're supposed to draw square brackets around this. Remember to do this now. You draw square brackets, and then you put a minus sign. And here's what that means. I have an NO3 group. That's what's in the brackets. And outside these brackets say, and somewhere floating around in there is a negative charge. Guess what you would do if this were like positive 2? You would do this, and then you would draw brackets, and you would put a 2 plus there. Okay, so you would show that charge. If you've got a charge there, a net charge left over, then there better be a net charge on your Lewis dot structure. Okay, so that's how you do those. You've now learned how to do those several times, how to do a NASA table, how to draw a skeleton, and your 2 notable exceptions. So let's see what we have. Okay, so that was your pre-lab. For some reason, the back page didn't get printed. Okay, so let's now look at your report form, what you're going to do here. So you know that. Now, I know this is a lot more space, but all you're going to do on this here is your NASA table. Okay, so all of this is just going to be your NASA table. Now here's what you're going to do. Now that's the first page that you're going to turn in. And then as you go to the next page, you're going to see there's 4 more items. So there's a total of 8. Starting with this, which is known as formaldehyde, carbon dioxide, okay, phosphorus trihydride, nitrate, beryllium dichloride, ammonium. Oh, there's a charge. You're going to correct for that. So you see carbon monoxide. Notice I have a note down there, so let me talk you through that. Although you have a binary compound, you're still going to consider carbon your central atom. And that means you may have something like this. Now this isn't correct, but it's going to be, because I don't want to give you the answer, but you're going to wind up with something like this. And so you're going to still consider, it's going to ask you questions about the central atom. Even though it's impossible to have a central atom with only 2 atoms, you're still going to do this and consider the least electronegative as the central atom. Okay, that's what happens when you have a diatomic molecule. You just pretend that the least electronegative one is the central atom. Okay, and this one, there's a lot of ways to arrange this. HCCH, so I tell you right there what the skeleton is. So I spot you the skeleton. You do the NASA table when you flesh it out. Okay, now look at part B. It's the same 8. So what I had you do is, part A is just the Lewis dot structure. So there's formaldehyde. Once you do that NASA table, then you're going to use that data to go to part B and fill out this part. Hope that's clear. And then when you do the NASA table for carbon dioxide, then you're going to use that table, and you're going to look back at that table, and then you're going to come finish this one out. This is the rest of your cascade, yes? And then you're going to see that the third one, yes, matches up with the third one, and so on. I heard a pop. Do we need to do the skeleton structure for page 144? Well, different people may have different manuals. Let me see what 144 is. Hang on. For 144, it just says NASA calculations. Okay. Don't have it memorized. 144. No, that's what I just said. That's this page here. That's this page. Yes? No, you just do the NASA. That's all that's what I said. It's wide, but you just do your NASA table here. That's all you need. Just follow the instructions. Just do the stinking NASA. Okay, table. Yes. Okay. It says just give NASA calculations. The next page. Yeah, same thing. You've got 8 you're doing. 1, 2, 3, 4, 5, 6, 7, 8. You need NASA tables for each of those, so you can take the same 8. 1, 2, 3, 4, 5, 6, 7, 8. They're the same 8. You're doing NASA calculations in part A, and then part B, you're taking all the information you did in part A, and you're fleshing out part B using your NASA tables. Does that make sense? Yes. Okay, good. Right. Okay, so that's how we're going to do. So that's kind of how you're going to do that. Right. Okay, so let's see. And then you'll do the post-lab questions. So when you upload these, be sure to follow the instructions carefully. In the task list of Module 11, it's going to give you explicit instructions, and it tells you exactly how to name files and what to do. If you don't name them right, look, that's part of being a college student, is being able to follow instructions, folks. So it's not being ticky-tack. If it says name something page 2 and you don't name it page 2, it's going to count off. In the real world, you can't do that. A nurse can't take somebody's chart and put somebody else's name on. You just can't make. You can't do that. You can't do that. You can't do that. You've got to do exactly what it says. Okay, so that's kind of how that's going to work. Okay, so now that you know, and then you do the post-lab question. So there's 5 pages, yes? So just to kind of go over to make it perfectly clear, okay? So that's your pre-lab, you're done. So this is going to be labeled page 1. That's going to be labeled page 2. That's going to be labeled page 3. That's going to be labeled page 4. And that's going to be labeled page 5. And then from those, you're going to take your images and convert them to PDF and then upload them. I've named the last 2 labs wrong. Eric, I don't know if there were instructions or not, but if there were instructions, there may not have been explicit instructions before. You'll have to go back and look. When we switched to online, I couldn't get every class done perfectly at front. So if I didn't tell you you had to name them a particular way, then you didn't have to. Okay? It's only... you just follow the task list. I'm only going to grade you on what I've asked you to do. So if there were not instructions earlier on how to name them, then you didn't have to worry about it. If it said upload the file, you just had to upload the file. So I'm not sure what they said a couple of weeks ago. I'm doing this for 8 classes all at the same time. So it's kind of, because I make mistakes, I don't hold any of the students accountable for anything I forgot to do. Right. Okay, so that's how that works. Okay, so what I want to do is then give you a, let me see, so what I could spot for you. Well, I shouldn't tell you this. Okay, so there's oh my gosh. Oops. I kind of screwed up on that one, didn't I? Or is this NO3? Shoot. I didn't mean to do that. One of these was supposed to be an NO2. Oh, boy, did y'all get away with one there. Okay, well, it looks like this one's done. You shouldn't miss that one, right? You shouldn't miss NO3. I think that's been done for you. Okay, as in just now. Okay. So remember, anytime, right before you do these, you're going to ask yourself 2 questions. What are you going to ask yourself? Is there anything smaller than carbon? In which case you're going to say for this one, yeah, there is. Yeah, there is. And then you look for any of those. Is there anything smaller than carbon? And at the same time, you're going to say, are there any charge on it? Is it an ion? And you're going to say, yeah, there is. So every time you ask yourself those 2 things, don't miss it, or everything else will be wrong. Okay. So having said that, now we need to learn what to do. So I'm assuming you can do that. Now we're going to do this. Okay. What you're really supposed to learn to do here. I cannot believe. Okay. Well, that dang sure does it. I got to get my Control Z back. Okay. So what you really do in the textbook is they tell you go from a Lewis dot structure, and then I want to know the electronic geometry, and then I want to know the molecular geometry. That's what you want to know. What I have added here is these 2 things here. These are the numbers. See, that little thing says a number. There's 2 numbers that you need to get all the way to molecular geometry. Once you have the Lewis dot structure, if you know what the areas of high electron density are, the number, you can do something to that number and it will tell you what the electronic geometry is. And then if you know the number of lone pairs, then you can go from here. So what I do is I kind of, to put a hook through your jaw and drag you across the finish line here, I'm going to not only make you tell me these things, but I'm going to make you tell me what number you use to get there. In other words, there's that cascade. So there's the Lewis dot structure. I'm going to make you give me Lewis dot structure. I'm going to make you tell me how many areas of high electron density you have right there. And then you use that to tell me what the electronic geometry. And then I'm going to make you tell me how many lone pairs you see. And then from that, I'm going to make you tell me the molecular geometry. So that's kind of what that's about. 3 of those are what you really want. 2 of them are pieces of data you need to get there. And that's what we're going to do now. Okay, lots of moving parts, lots of things to remember. But hey, you get a cheat sheet. I mean, for Pete's sake. It's not even like you got to memorize it. Just practice it till you can do these quickly. You'll have to do these quickly on the exam. Okay. Right. So let's look at the next thing. Let's see. That's what we worked in class. That's what we worked. Okay. So let's do the next thing you need to know. So once you have the Lewis dot structure, like this, what is the next question is, what is the electronic geometry of that? See, I just drew it like a flat pancake. Now somebody else could have drawn 1 oxygen there and 1 there, and they could have put their 3rd one up here. Remember, a Lewis dot structure just tells you what's bonded to what. It doesn't say anything about the angles or anything. You can draw this any way you want. It's a 2-dimensional structure. What this tells you is there's a nitrogen that's double bonded to an oxygen and it's single bonded to another one. It doesn't tell you anything about the angles. I can draw it any way I want. But that's what this is going to give me. So, electronic geometry, what is that? Okay, that's just looking at the bonds. Remember, electrons make bonds. It's just looking at the bonds that make up this molecule. It's ignoring what's on the outside edge of it. It doesn't care about what's on the outside edge. Okay, so right now we're going to look at, let's just go ahead and do nitrate ion. Okay, so I have a nitrogen and 3 oxygens. So what are they shaped? Is this thing shaped like a pancake to where it's kind of shaped like this? Or is it shaped like a pyramid? You know, those 3. See, you got the central atom, and you got three things and hanging off of it. I don't know. How are they structured? All I know is I have a central atom and three things hanging off. But I have no idea at what angle or anything they're hanging off. But I need to know that, because something that's shaped like this, like a pyramid, is going to behave very different from, or maybe it's shaped like a T. Maybe it's shaped like that. There's my central atom, see? There's a T shape, there's a, whatever that thing is, a planar triangle, and here's something that looks like a pyramid. So, so how's it shaped? Well, that's what we want to know. So these bonds, that's what it means by electronic geometry, because these are the electrons pairs, and I want to know how far they are apart. Okay, so here we go. Electron pairs. First thing you need to know is count the areas of high electron density. So what is, pray tell, an area of high electron density? Okay. An area of high electron density is any single bond or double bond or triple bond or lone pair. So you need to know that. What is an area of high electron density? An area of high electron density, again, is any single bond, any double bond, any triple bond, or any lone pair. I guess I'll just do two of them. Here, I'll circle it and make it so you can see it. Yes? That is, any one of those counts as an area of high electron density. Okay, so let's try something here and see if you can get this. Okay, let me move this up here, and let me get me a little writing tablet here, and let's write with this thing here. Okay, so first of all, let's define, let's look at this. Okay, I'm going to look at, it's GoodNotes that's causing me the problems, isn't it? Okay. Let me try that one more time. Undo pen stroke again. It's not going to do it. Not going to do it. Okay. Forget that. This thing won't let me erase. Okay, so I'm going to have that. I'm going to look at this. That's called a double bond. That's called a triple bond. And that's what a lone pair looks like. Okay. So I'm going to teach you a very important distinction between these, because here's what's happening. We've been talking about three things. We've been talking about electrons. We've been talking about pairs of things, electron pairs, yes? And then I keep throwing the word bonds out. And they're all interrelated, but they're very different things. And they're talked about at different times. So let me kind of work down on this. A single strike mark, a single bond, and this is called, by the way, this is called a single bond. This is called a double bond. This is called a triple bond. And this is called a lone pair in official chemistry lore. Okay, so let's go back and let's look at this thing. And I want to differentiate. I want to make it real clear here. The difference between an electron and an electron pair and a bond. How many electrons is there in a single bond? And by the way, single bond means there's some atom on this side of it and there's some atom on that side of it. Okay, so let's see, a single bond. So how many electrons does this represent? 2 electrons. Yes? How many pairs is that? It's 1 pair, right? 2 pairs of it takes a pair of electrons to make 1 bonding pair. How many bonds is this? It's 1 bond. It's 1 single bond. So far, so good. So I'll look. I'll wait just a second. Are there any questions on that? No. Okay, here we go. Switch colors. Okay. How many electrons are in this double bond? 4. Really? Yep. It's got 2 bonding pairs, and each bonding pair has 2 for a total of 4. How many pairs is here? How many bonding pairs do I have? Well, duh, I could see 2. So here's the big question. Don't have to answer. I want you to answer it in your. I'll give you 5 seconds to answer this in your own head. How many bonds does this have? 5, 4, 3, 2, 1. It's 1 bond. It's 1 double bond. It's 2 bonding pairs. It's 4 electrons. That's key. Here's why. Because the NASA table has you deal with electrons. Has you count electrons. That's what we're doing at first with the needs and available. But to make the Lewis dot structure, it deals with pairs. But then I'm telling you an area of high electron density is how many bonds. So you have to be able to shift gears. This is the table. This is the Lewis dot structure. And this is the molecular and electronic geometry. And this is why this works. It's a progression that pulls you up. Okay, so let's, now, good. Fortunately for you, there's only 3 types of bonds in the world. Single bonds, double bonds, and triple bonds, and lone pairs. So this list doesn't grow any longer. It's pretty, okay. So let's look at a triple bond. How many electrons are there? I'm going to go with 6. Why? 1, 2, 3, 4. So remember, each stripe mark represents what? A single bonding pair. Okay, how many bonding pairs are there? 3. How many bonds are there? 1. That's 1 triple bond. So it's true. Some bonds are made up of 2 electrons. Some bonds are made up of 4 electrons. And some bonds are made up of 6 electrons. How do we know? Well, we look to see how many electrons are there. Okay. A lone pair. A lone pair. How many electrons? Well, 2. Of course. How many pairs? Well, it's a lone pair. It's 1. How many bonds is this? It ain't no bonds. It's not a bond. It's a lone pair. That's what it means, alone. Okay. Here's the last thing you need to know. So how many, each of these, how many areas of high electron density is each one? And the definition is of an area of high electron to any flavor of bond or a lone pair. So if you see one of those, you got to count that as one area of high electron density. If you see any of these, for every one of these you see, you count another 1. For every one of these you see, you count another 1. And for every lone pair you see, you count it as 1. This is what you need to see right there. This is what determines the electronic geometry. Ready? So why it calls area of high electron density, see, even though these are 2, they're all grouped together to make one area. And these are all grouped together in an area. And all 3 of these will be grouped together to make one area. And these will be together to make an area. So even though they have different number of electrons and different number of pairs, and they may or may not be involved in a bond, each of the areas of high electron density, each of these represents an area that is very dense in electrons. And that's why each of these counts as 1. Okay, so let's do our nitrate. Might as well go ahead and do one. I guess you get a freebie here today. Okay, so we already did the Lewis dot structure. So how many of area of high electron densities are about our structure here? Where was our structure? We drew it over here. Okay, so how many area of high electron density do you see? Well, let's see about that. My highlighter. Okay, how many do we see? Oh, by the way, this is about the central atom. When you do this, when you count these, see that ACA? Boy, don't lose that. That's key. That means, that's my abbreviation to remind you, about the central atom. The Lewis dot structure looks at the entire molecule. When you then focus on the geometry, you're only looking at the geometry about the central atom. That's what controls. About the central atom. Probably another one of the most missed things. They just count everything. Okay, so here we go. So about the central atom, let's highlight that. There's the central atom we got, right? Okay. So let's look at everything about the central atom. I want to look at all these bonds and lone pairs. See, if I had thrown any lone pairs on the central atom, right, they would be there. Okay, so what I'm doing is I'm going to put a big fat circle around my central atom. Now I'm going to count areas of high electron density. Ready? Let's count. And I do what's called the four count, F-O-U-R. I count single bonds, I count double bonds, I count triple bonds, and I count lone pairs, and I look at how many fingers I have up, and that's how many there are. The good news is in this class, you're never going to get more than 4. Here we go. How many single bonds do you see? 1, 2. So far, I have 2 areas of high electron density. I'll keep marking down there. I got 2 areas of high electron density. How many double bonds do I see? 1 double bond. For those of you who are counting pairs, you're going to miss it because you're going to think that's 2. That's what? 1 double bond. That's a double bond. It counts as 1 area of high electron density. That's 3. How many triple bonds do I see? None. And finally, how many lone pairs do I see? About the central atom, I see a whole bunch of lone pairs, but how many do I see about the central atom? And the answer is none. Okay, so I've gone down my list. I've checked for all of these. How many do I have? 3. So I have 3 areas of high electron density.